We're going to cover a couple of examples on how to determine the compliance matrix and calculate stresses and strain for various situations. And I'll keep it very simple. In general, we have to relate stress and strain. The stress has to be related to strain, and we do that through this constitutive relationship for orthotropic properties. That's for a single lamina, and that's in the local orientation system of that ply. So if this ply looks like this, there's a one direction, two direction, and three direction. E11 here represents the modulus in this direction. E22 represents the modulus in this direction. E33 represents the modulus in this direction. And then you have the Poisson ratios. If you pull in the one direction, the two direction contracts, and so forth. And so let's choose an example here. So we find that we want to determine this data. We have no testing. So, but we want to estimate it because we're early in the design process. We have to start with something. And microscopy was used from experience, and 70% volume fractions was found. Typically, void content 4%. So the void content is 4%, and the fiber volume content is 70%. Then the resin volume content is 100 minus 7, 70 minus 4. And that's 26%. Now I'm giving the T700G fiber system. And for that, what I'm going to do, I'm going to look at the literature. Okay, we're going to look at the literature and determine what that could be. And then I go to the Torre Composite Materials America, and I find that T700G is 34.8, the modulus, shear modulus, tensile modulus. And I can click here in the view data spec sheet and see more data here. And I see that the tensile modulus is 34.8. And they provide other composite properties if this was within a resin system. So it tells you estimated properties if this was within a resin system, which can be very useful. But for now, we're going to choose 35 MSI as a starting point. And so for T700G, the modulus of fiber is 35 MSI. And we don't know the Poisson ratio, but we could assume it's somewhere in the 0.35 range. Not 100% accurate, but it's a good starting point. And then we have the matrix. And by the way, we don't have to even use this data. We don't need this, but we could if we wanted to. Since I didn't give the shear modulus, that's where it could be useful. So I'll just give it for now. And then we have to find the modulus of the matrix. And for that, we go to the Hexcel website, and then we look for the epoxy of interest, which is 3501-6. So I click here and I get the data spec sheet. Poisson ratio in the 0.36 right here, and then the tensile modulus 0.615. So we'll just transfer that information over. Okay, so we'll just put that in there. And now we are ready to estimate the different values for E11 and so forth. So for E11, we can use the rule of mixtures. So the rule of mixtures will be used. And that's for the void. The void has there's no modulus, so that goes to 0. But I get 35.7 plus EM, which is 0.61 times nu M, the volume fraction of the matrix. I apologize, that's incorrect. The volume fraction of the matrix was found to be 26%. And then I'll just quickly calculate that in a calculator. I'm doing it quick. So 35.7 and 0.61 times 0.26. And I get 24.7 MSI for that one. And then likewise, I can then calculate what E22 could be. And to determine E22, we can just use the formulas that we already previously discussed in a previous lecture. And E22 will be EF, EM divided by volume fraction of the matrix times EF by that. And we can do a calculation fairly quickly. And I'm doing it here real time. And I got 1.67 MSI, which is reasonable. And this is a unidirectional lamina. And so therefore E33 should also be equal to 1.67 MSI, or approximately equal, not exactly equal. And we know that because we discussed previously for unidirectional lamina, E22 will be equal to E33. And we're not provided nu 1, 2. We could try to estimate it, but we could also make the assumption that nu 1, 2 will be close to 0.35. We could try to determine what it is using the rule of mixtures as well. we have the Poisson ratio here and the Poisson ratio there. So we could try to estimate what that looks like for the composite. But we could also use the fact that gave us guidelines that nu1 2 will typically be equal to nu1 3 equal to 0.35. In our case, nu2 3 is a racing dominated property, and in that direction we have the matrix dominating that, so 0.36 makes sense. And then I can continue on. Now I have to calculate the shear modulus of the fiber, the shear modulus of the matrix, and then I can use the formula for G12 to estimate. You're just estimating G12 using the rule of matrix again. And I already covered how you could do that in a previous lecture. So again, G12 will be equal to G13. And you can estimate it by GF divided by GM. And then we have GM times the volume fraction of the fiber, volume fraction of the matrix. And then you have, you can calculate that very quickly. I won't do it now. And then G23 typically is about, somewhere between 0.5 to 0.7 times G13 or G12. But that's harder to estimate. It's just an approximation what we've done here. So once I have all this information, and I'm asked to calculate the compliance matrix, use the compliance matrix. All I have to do then is plug this in. I have them all. And it's an approximation. With no test data, you're able to get something going. You see here, nu21 and nu1, so they're different. So nu21 divided by E22 equals nu12 divided by E11. I have this one, I have this one, I have this one. So I can calculate this one. Because the compliance matrix is symmetric. So this term should be equal to this term, for example. This term should be equal to that term, and so forth. So yeah, you can quickly calculate compliance matrix, and I hope this example helps. In this example now, I'm going to look at a filament wound composite. And this angle is theta. And it's a closed vessel, pressurized. The vessel has some internal diameter, D, and it's pressurized to P. And we want to determine the shear and normal forces per unit length of the filament wound. And we're given properties. We're given E11, we're given E22, for example. We're given G12 and nu12. I don't know if it matters that we're given that information, but the important thing here is I can now, if the thickness of this filament wound was H, and this is a pressure vessel, by the way, so I have pressure applied inside with closed ends. Then if this is the X direction, and this is the hoop direction, hoop axial, then sigma XX equals the pressure inside the vessel times D, the diameter, divided by 4H. That's the axial stress. And the hoop stress is PD divided by 2H. And that comes from formulas from books, mechanics and materials. Okay, so you can calculate that. So if this is given to you, this is given to you, the diameter was given to you, I can calculate these stresses fairly simply. And now all I have to do is use the formulas the transformation formulas. And the transformation formulas are simply sigma 2. We discussed those before. And then we have sigma 1, 2. I discussed these formulas before, and I know theta. This angle theta will be given, so I can plug it in here. I know sigma xy is 0 in this example, so this goes away. There's no shear when you have a vessel in a hoop, but you will get shear in that plane along here. And then the formula for sigma 1, 1 I also had given. So with this information, you can calculate the stresses along the fiber, that's sigma 1, 1, across the fiber, and then the shear for a square oriented along the fiber direction. And so that should help with some of the problems that we're working through.